Alright, grade 12 chemistry. This is a video about ethers and esters. Should be a pretty short one because it's just two functional groups to talk about. Here's what we're going to talk about today. We're going to talk about condensation reactions, which is the reaction that creates both ethers and esters. We'll talk about naming the ethers. We'll talk about the esters, a little bit about the 8 ending. You might have seen 8 endings, properties, and then hydrolysis reactions, which are going the other way. Turning the ether or ester back into their constituents. Alright, jump into it. This is our third reaction that involves alcohols. You might notice that alcohols take part in a lot of these different reactions. That's because, the OH group is a very active kind of group. If we take an alcohol and we make it react with another alcohol with the right conditions, what we can do is pull out a water. Notice that this OH met this H and then the water comes out. Now water is a very common molecule. It's a very low energy molecule. It's a very stable molecule. So if you can make water in a reaction, often you will. And it creates all kinds of interesting reactions. We'll see more of that in, the third unit, thermochemistry. Water's so stable that it's relatively easy to pull it out of something. So we pull out the water. What's left over is this oxygen, this green oxygen. And the green oxygen actually just attaches to this carbon here. So we end up with what we call an ether. So note that this oxygen is now connected to 2 carbons. I like to call that an oxygen bridge, like a bridge. So that's an ether. This is called condensation, which is a great name. I love the name condensation because it kind of has 2 meanings in English, and both meanings actually work for this for this reaction. Number 1, condensation is when like water ends up on like a cold glass, right? That's condensation on the glass. Hey, water comes out, right? So hey, number 1, condensation. You can think water comes out. Number 2, condensation. To condense means to make smaller, to bring together, and that's what happens here too. You have an ethanol and an ethyl. They come together into diethyl ether. The two have become one molecule, so it's been condensed. So you end up condensation by 2 meanings of the word, which I think is really, really neat. Now you might think, oh, water. We've seen water come out before. We've seen an alcohol give us water. We called that an elimination reaction. Well, that created an alkene, right? It took the alcohol and it took away an OH and an H off of the same molecule, left behind a double bond. That's elimination reaction, but elimination reaction just took the water away, didn't do anything else. Condensation is considered a different class because we're also bringing these 2 together. So that's the difference between condensation and elimination. Here's an example of it. Here's methanol and propanol, 1 propanol, 1, 2, 3, 4, actually 1, 2, 3, 4, this is butanol, and you'll end up with an ether where one side has 1 carbon, the other side has 4. 1, 2, 3, 4. Right, so the 1 carbon and the other carbon, and there's this oxygen bridge, and you've made H2O as a byproduct. Now, you might remember in elimination, we used sulfuric acid or phosphoric acid to pull out the water. We do the same thing. We use sulfuric acid or phosphoric acid, but there is a small difference. You use a slightly colder temperature than dehydration. Dehydration, we want to rip the water away very quickly, make that double bond. Here, we want to keep some of that oxygen around to make the condensation. So we do it at a colder temperature. This is just a general guideline, like different ethers and different alcohols will take different temperatures in order to do it. But yeah, typically a colder temperature. There's other ways to do condensation reactions as well. Some, for example, are done in weak acids. It is very hard to get a specific product unless you have identical alcohols to start with. Why? Why? Well, what's stopping the methanol from hooking into another methanol, right? If you have the methanol attached to another methanol, you just end up with, this kind of thing. with an oxygen in the middle. Like if two of those met up, remember we have billions of these in our solution, so if two of those met up, you just end up with this dimethyl ether. Or if two of these ended up together, I'm just going to draw it here, right? You'd end up with something like this. 1, 2, 3, 4, yeah. 1, 2, 3, 4, yeah. So you know, if two of these ended up together, you get this. Two of these ended up together, you get this. So you kind of get a mix of a bunch of different ethers if you tried it. So yeah, it's hard to get a specific product unless you have two identical alcohols to start. Two identical alcohols to start with. But that's a condensation reaction. So hopefully you understand condensation reactions now and why they're different than elimination reactions. Okay, naming ethers. There's actually kind of two schools of thought. Simple ethers like this can just be named based on what the two side chains are. So this is diethyl ether, diethyl ether. But IUPAC would prefer us to call it ethoxyethane. Or over here we have right? We have ethoxy propane or ethyl propyl ether. If we use the common name, I mean, you can see where that comes from. It's ethyl and propyl, ethyl propyl ether. But in IUPAC, this is an interesting one because ethers are actually lower priority than alkanes. So if we looked at our priority list here, ethers are down here below alkane, so the naming is kind of interesting. What happens is it becomes a side chain, kind of like a chloro or a bromo or one of those groups, or like a methyl group or something, but it just becomes an oxy group. So this propane is our main chain, 1, 2, 3, and on number 1, we call this a side chain, an ether side chain. It becomes 1 ethoxy. Like if this was a chlorine, it would be 1 chloropropane. It just becomes 1 ethoxypropane. It's a side chain. If it were on 2, it would be 2 ethoxypropane, right? It's the same side chain, ethoxy, but now it's on 2 of our propane rather than 1, and so that's how we name it. They have numbering priority over halides, but I think it's actually the same numbering priority all the way through, as long as it's an ane ending. They're obviously below alkenes, alkynes, alcohols, and all the other things because it's still named as an ane. So it's the same thing. Find your longest carbon chain, and then the shorter side is going to be your ether, and that's how we name an ether. Let's take a quick little dive over to this guy, and we're going to name an ether. I should change the current topic, naming ethers. Okay, naming ethers, and keep in mind ethers. Okay, ethers are named as an alkoxy side chain. So let's just, let's just throw something together. We'll do something like this. We'll stick an ether on there. Let's do that. So here's some kind of molecule. It's clearly an ether. How do we name it? Well, we have our main chain here. Our main chain, we'll start numbering from there because it'll give the ether the lowest number, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then this ether is on 3. So it's 7. It's all single bonds. So this is heptane. And then we need this ether here, which has 2 carbons on it, to be a side chain, something oxy, right? Something oxy. What oxy? Well, it is ethoxy, heptane, and it is on 3. So this is called 3-ethoxyheptane. Okay, and that 3-ethoxy is that group right there. Yeah. Let's pretend we had, carboxylic acid on here. Right? That would be heptane, 3-ethoxyheptanoic acid. Stuff like that. You can get into some really interesting ones like this, and remember that priority is still priority. So let's try a slightly more complicated one. I'm going to draw something like, let's do something like this. Right? Like this. And then we'll do an oxygen here. Yeah, that makes sense. So this is an interesting one because we have more carbons on this side, but over here we have a higher priority group, this ketone over here. So this ketone is going to take our priority for our number. And actually, you know what? I'm going to fix this up a tiny bit. I'm going to do something like this, just to give the ketone, just to make it more obvious. Right, so we have 1, 2, 3, 4, 5 carbons on this side, but only 1, 2, 3, 4 carbons on this side. But the higher priority here is the ketone. So we're going to name this as an one. We know that the ending is going to be an one ending. Which one? Well, we'll start numbering closest to the ketone. 1, 2, 3, 4. It's a butanone. Butanone, because and for all of the single bonds. Butanone. It's a butan 2-one, actually, butan 2-one, because that's where the ketone is. And then on 4, we have this group. We have this side chain of 1, 2, 3, 4, 5. So it's a 4 pent, because there's 5 carbons there, 1, 2, 3, 4, 5, 4 pentoxy butan 2-one. So ethers are always named as a side chain. And all the other rules still apply. You might be wondering what happens if I have, I don't know, a side chain on my ether, like that. Well, in that case, you have to name this guy, and then the whole thing gets an oxy. So it's like, it's still on 4, because it's on 4 of this chain here, right? But then you have kind of, this is 1, 2, 3, 4, 5. So it'd be 4, 2 pentoxy butan 2-one. Would put those together. You have to put those together. So you got 2 methyl pentoxy, 2 methyl pentoxy butan 2-on. Stuff like that. You can use brackets. Yeah. To make it work. So yeah, that's how you name an ether. Yeah, that's naming ethers. Let's jump back over to here. We are going to get into esters. So esterification. And here's carboxylic plus alcohol equals ester. So esters. Esters are very, very cool. They're also formed in a condensation reaction. Okay, because we have an OH here and an OH here. So the OH is going to meet the H. Those are going to go away. We're going to leave the oxygen. So know that the oxygen is still here, one of the oxygens. We have water that came out. There's the water that came out. But please note that that double bond still exists up here, right? And we always know which one was the acid. We know which acid, which one was the acid, because that's the side that had the double bond, right? The acid's on this side, and the alcohol's, the thing that was the alcohol was on the other side. So you can kind of like draw a line through the oxygen. You know that one side was the acid and the other side was the alcohol, the original alcohol that made this condensation reaction. Similar conditions, just some heat and some sulfuric acid will give you an ester. Doesn't even have to be very hot. In the lab, we do it at like 60, 70 degrees Celsius. It's really, this is a very common reaction to do in an organic lab. So that's a thing. You always get the product you're after because one side's always the alcohol, the other side's the acid. You might get some side reactions, some condensation between two alcohols, but if you don't let it get too hot, that's not going to happen. Your acid is much more likely to condense with your alcohol, and you make an ester. They're very interesting. Naming esters. Naming esters is relatively easy because you've always got an alcohol on one side and a carboxylic acid on the other. So you literally just name the alcohol and name the carboxylic acid, and then you put those two names together. Here's how it works. First off, esters have the second highest priority. So if you have an ester, you're going to name it as an ester. You can see that here. Here's the esters, the second highest priority. And here's the rule. The rule is you name the alcohol. So literally just name the alcohol as if you're just naming it. Name the carboxylic acid as if you're just naming the carboxylic acid. And then what you have is the alcohol group gets an -il ending, and the acid group gets an -08 ending. So here's propyl pentanoate. You can see the propyl, because 1, 2, 3, this would be propanol. Pentanoate. And the pentanoate is the 5 carbons on this side. Now please note that that's a carbon. A lot of people mess this up and forget that that's a carbon there. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that is propyl pentanoate as an ester. There's also a space. There's a space between them, and that's how you can do side chains on your esters. So we are going to, let's just name an ester. And again, let's just show off that, name the alcohol, name the ester thing. All right, so let's make an ester. Right, let's do something like that. We'll put a chlorine on here, and we'll stick, I don't know, a methyl group over there. All right, something like that. So, which side's the alcohol, which side's the carboxylic acid? Well, we can split it right down the middle, and we can name one side and the other side. So this alcohol would be 1, 2, 3, 4. It's a butanol. It's a 2-methyl butanol. Right? It's a 2-methyl butanol on this side. This side, right? The carboxylic acid side would be a 1, 2, 3 propanoic acid. Right, and it's a 2-chloro, so it's a 2-chloropropanoic acid. We put those two together. We have to put those two names together. The butanol, right? If we go back to here, right, -08. The butanol will become 2-methyl butyl. There's a space, and then we write the acid, and we finish it with -08 instead of oic acid. So 2-methyl butyl, 2-chloropropanoate. And the space tells us whether it was with the alcohol or with the acid, which side chain is with which one, right? These are both say 2, but this 2 is on this word, which means it's with the alcohol side, and this 2 is with this word, which means it's on the ester side. So that's how we name esters. Next part was just a quick note on 8 endings. 8 endings suggest that it's an anion that came from an ic acid. So nitric acid makes nitrate, acetic acid makes acetate, glutamic acid here makes glutamate. You might have heard of monosodium glutamate, right? So glutamate, or benzoate, which is benzoic acid, benzene with a carboxylic acid, benzoic acid, but it's an anion of benzoic acid. So yeah, that's where the 8 comes from naming esters, this O8. It's just saying that that's where the acid came from. So you can think of like nitrate with nitric acid and stuff like that. So that's 8 endings. And then some properties. So ethers and esters can't hydrogen bond. Right? They can't hydrogen bond, but they can accept hydrogen bonds. So they have those lone pairs on the oxygen, so water can coordinate to them and stuff like that. They can accept hydrogen bonds, they just can't make their own. So they kind of get these intermediate properties, Typically, they'll have relatively low boiling points and low vapor pressures. We call that being volatile. A lot of people get this wrong idea about volatility. Volatile doesn't mean like they're going to explode. Volatile in chemistry means that they make a vapor very easily. They very easily spread out through the air. So ethers and esters typically will kind of be smelly because there will be a lot of it in the air. They're also generally flammable, which leads to some safety concerns because there's a flammable vapor that's easily being released into the air. That's why volatile gets this kind of reputation for meaning explosive. It's because you've got this vapor in the air mixed nicely with all that oxygen and it'll blow up. But volatile really means only that they are easily dispersed through the air. They have this low vapor pressure. They make good solvents because there's some polar character and some non-polar characters. They can kind of like attach to a variety of different things, especially in organic chemistry where we're working with a lot of non-polar compounds, things with long carbon tails. Ethers make really nice solvents. Esters, same kind of thing. They usually don't dissolve in water because they're kind of bulky, but they will dissolve in alcohols relatively well. Again, the extra little carbon stuff, the organic nature of the alcohol will help them dissolve. And the cool thing about esters, the really cool thing about them, is that they smell fruity. A lot of small esters will smell fruity. So here's the alcohol and here's the carboxylic acid. You can see, for example, that propyl methanoate smells like apples, or butyl methanoate smells like strawberries, and all these other ones, pineapple and citrus and, mushrooms, I guess, apparently. Very strong blackberry smell. So yeah, you get a lot of artificial scents from esters. And they're used in perfumes and things like that. And the volatility really helps there, right? The fact that they go up into the air very easily helps them make those smells. So yeah, those are some properties of ethers and esters. And the last piece is hydrolysis. All right, hydrolysis. We can't change. So one thing to keep in mind when we talk about these reactions is we never change carbon backbones. Carbon backbones. All right. So hydrolysis reactions are the opposite of condensation. We add water and then we split it. All right. So here's an ester, double bond oxygen, oxygen bridge, and then the rest of the molecule. Typically, this is done with a strong base. It can be done with a strong acid as well. So here's one with a base, here's one with an acid. You get a carboxylate, right, 8 ending for the acid, and an alcohol that's got sodium, just kind of a positive sodium hanging out next to it. If you then add an acid, if you protonate it, you can add the hydrogen back. It's called an acid-base workup. Or this one here, if you add a strong acid, you can break it into an OH, and then the iodine is hanging out with the methyl group that was on this thing. Or this guy with HI, it'll break it up and break it up. One thing to note, we can't change carbon backbones, so the 2 carbons and the 2 carbons are still 2 carbons and 2 carbons. This benzene is still a benzene, this single carbon is still a single carbon. We're never going to, in our course, crack any carbons in half. And here's one with an acid, an H2SO4. You can actually crack the ether a half. One thing you can actually do, you can see this yourself if you find an aspirin bottle. Aspirin is acetyl salicylic acid, and it is actually an ester. And it will actually self-hydrolyze because it's an acid and it's also an ester. So it'll actually hydrolyze itself, releasing acetic acid. So often aspirin bottles will smell like vinegar because you've got this acetic acid coming off of them. You've got acetate coming off. That's it for ethers and esters. Let's just review what we talked about. Condensation reactions, 2 alcohols get together, make an ether. An alcohol and a carboxylic acid get together, they make an ester. Talked about naming ethers. They have lower priority than alkanes, so they just get named as a substituent all the time. We talked about esterification and naming esters. Now esters actually get a priority, they're second in priority, and they get that two-part name, alcohol then acid. Talk about the 8 ending, which is just generally an anion that came from an acid. Talk about properties. Esters are smelly, ethers are smelly. They're both volatile and low boiling point. And then hydrolysis reactions, taking it the other way, just cracking it down the middle with a strong base or a strong acid. That's it. We'll do lots of practice with this, and we'll see you guys in class. This was a really short video.